Hello, everyone. I have the privilege to introduce our first keynote speaker, Chris Jackson. So Chris is the Equinor Professor of Basin Analysis at Imperial College. And having completed his BSc and PhD at the University of Manchester, Chris was employed as an exploration research geologist in the Norsk Hydro, which is now Equinor Research Centre in Bergen. And since moving to Imperial College in 2004, Chris's research has focused mainly on using traditional fieldwork techniques and seismic reflection data to study the tectonostratigraphic analysis of sedimentary basins. And today, Chris will be talking about the kinematics and structure of submarine landslides, recent learnings from 3D seismic reflection data. So with that, I'll pass it over to Chris.
Thank you, Benita. I'm going to hop into here. Is that all good? Look for a few nods. Okay, great. Thank you. Yeah. No, it's a huge pleasure to talk about stuff I like all the time anyway, but especially here at the NSRG event as well. So I'm going to talk today about quantifying the kinematics and mechanics of subaqueous landsliding using subsurface data. I sort of tweaked the title to fit in with the experimental quantitative and numerical sedimentology theme of this afternoon's set of talks. And what I'm really going to do today is like highlight and celebrate the work of some amazing early career researchers I've been lucky enough to work with over the last few years, Harrier, Mike and Nan, and then the kind of associated people who work with them. And just to show you some of the work that they've done in this area of submarine landsliding. So what are slides? I think many of you on the call already know what they are. So these are a type of sediment gravity current. They're characterized by relatively high levels of cohesion and involve a range of processes like creeps, slides, and debris flow. These sorts of deposits or these sorts of events can occur both in lakes and in the marine realm. Hence, we refer to them as subaqueous rather than submarine landslides. And as you can see in this diagram in here, if I just flick to the laser pointer, you can see that they're characterized by this basal lower surface, which we refer to as the basal shear surface. They have this rather rugose or undulose upper surface. And internally, they're characterized by a range of different types of features. So we have blocks and fold and thrust belts down here. The main thing to take from here is the three main kinematic domains. There's an area of an extension up dip, where we have normal faults. We have an area of translation in the middle zone here, which is where the body is moving down slope, and then a toe domain or a contractional domain down dip where we have bulk horizontal shortening. So how can and how do we quantify slides? Well, we can measure a bunch of stuff, okay? So as you can see in the cross section here, we can measure, for example, the deposit thickness as well as the deposit length. If we have access to things beyond simply a cross section, so we go from outcropping to geophysical data or bathymetric data, remote sensing data, we may get a plan view image of these deposits. And as you can see here, we could measure something like width. And if we have access to width and length and thickness, we can obviously then measure area. And because we like measuring things, we can then come up with graphs like this, which actually have quite a lot of predictive power. We can plot area versus length here, and we can actually try to work out one of the parameters from one of the other, one of the unnamed parameters from one of the named parameters as well, and back out these rather strong correlations. We can also look at the recurrence intervals of slides, and that's important for the next slide I'm going to show. So in terms of recurrence interval in this graph here, we're looking at time before present from 0, going back to 150,000 years on the x-axis on the right, and then relative sea level, which is the red curve shown in here. And we can see a number of submarine landslides plotted in through here. And you can try and then see how often those submarine landslides occur, whether they correlate with things like earthquakes or changes in sea level. And that's important, as shown in the next slide, because if we're considering the geohazard potential of these sorts of events, we obviously want to know how big they are and when they're likely to happen, because they can generate things like tsunamis, which obviously can negatively impact human life, but also pose a threat to subsurface or subsea infrastructure, so cables and so forth. So there's a real reason in terms of geohazards we want to understand slides and actually quantify quite a lot about them. Also, in terms of carbon storage, we may actually sequester quite a lot of carbon material within these sediments before they slide, but also by having these slide events themselves, we can actually liberate that carbon and allow them to go back into the water column. So knowing when that's likely to happen and what the yield of carbon from those slides is going to be is really important. We may also, from a petroleum point of view, want to understand how these bodies may behave, because they can, in some instances, act as seals. So what I'm showing you here is depth on the y-axis, and I'm showing you formation, pressure, and bars on the y-axis, on the x-axis, and this is from the Magnus Field in the North Sea. As you can see, the pressure is increasing in the upper reservoir in these turbidites before taking a big step to the right, which is the overpressure into the lower reservoir, which is a turbidite. And that's all being driven by a debrite or a mass transport complex or a submarine landslide that's not very thick at all, a few meters to 10 meters thick, but it's controlling a huge amount of compartmentalization of that reservoir. So we want to know how big those things are. So if we know it's that thick, how aerially extensive might we think this deposit is, if we can establish relationships like we saw in the previous slide. So we want to understand how slide size and how the slide sizes can change through time. We want to look at things like intra and sub-slide strain and how that varies spatially within the deposit, and how the petrophysical properties of slides relate to their emplacement mechanisms as well. And what data can we use then to quantify these different aspects of slides? So on the x-axis here, we have an aerial resolution. So think of that as like in map view. And here on the y-axis, we have vertical resolution, and 10 to the 1 is 1 meter. So 1 meter's in here. And we can see these different types of data going from core and thick sections up to seismic reflection and potential field data. So these data are great for submarine landslides or subaqueous landslides. You know, seismic data allows us to look at things on the regional scale. We get out the big morphology and distribution of these bodies and their stratigraphic occurrence through very thick successions of strata in sedimentary basins. Outcrops are good because they allow us to zoom in to tens of meters to a few kilometers in scale and really get our hands on the sedimentology and the depositional processes occurring within these deposit types. And then if we go to core and log data, we go down to the smallest scale, just here where there's a star in the bottom left of the graph. And you can see here, using these petrophysical data, these well logs, we can get to the petrophysical properties as well as the lithology and the depositional processes. So given all that, what are the outstanding questions? What am I going to talk through now? So we can quantify intra and subslide strain. You know, can we do that? Can we actually put some numbers on things? And how might this knowledge help us improve our understanding of the geohazards and different aspects of resource extraction and sequestration? So in this talk, we're going to go through a couple of things. We're going to look at longitudinal strain within mass transport complexes, or these slides, I'll just call them, and vertical strain. And that will be looking at seismic reflection data sets. And then we'll also be looking at erosivity and deformation. So what happens in that critical basal zone as the material is moving across the seabed? So let's start off with some of Mike Stevenson's work from offshore Uruguay. This is a submarine landslide in here. This is from the marine realm. We can see the basal shear surface is highlighted in yellow in here, and it's very erosive. We can see three main domains within this body: an area of extension, up dip, and normal faulting. We can see a translational zone in here, which in map view has rafted blocks and shear zones, not very well expressed here in 2D section. And then we have the compressional domain in here, where we have this rather exquisite fold and thrust system in the distal area with this frontally emergent zone. So how can we quantify the strain occurring within that body simply beyond saying that there are these different structural domains? Well, what we did is we took a depth section. So we had a depth migrated seismic volume, which Mike interpreted in great detail. You then can decompact that. So we can remove these paler overburden layers in here and decompact the stratigraphy. We then can map internal horizons, and that internal horizon is going to be important for quantifying the strain in this example. We then can put that at 1-to-1 to give you a real sense as to what the body geometry looks like. And then obviously we can measure the fault heaves in the extensional domain to look at the amount of stretching. We can also measure the amount of thrust overlaps in the compressional domain to look at the amount of shortening, and then we can compare the two. By doing that in the extensional domain up in here, we see the present length of the section. So this is HE, is 13.9 kilometers, but the restored length is 12 to 12.3. And so that yields this amount of extension in the up dip area. So an extension amount of about 13 to 16%. And some of that may, of course, be accommodated by subseismic faults and some other things I'll come on to. In the contactional domain, the present length of the contactional domain using this internal horizon is about 32.3 kilometers. And the restored length, when you pull everything back out, goes up to about 40 kilometers, yielding a shortening, which should be, that should say percentage here, 17 to 19% shortening, or this amount in kilometers. And I'll come back to what we think the mechanisms are in a minute. And that yields a discrepancy of about 5.1 to 5.9 kilometers. So that means that there is more contraction, sorry, there's more contraction than there seems to be extension in here. So why is that? If we then think a bit more about that distal domain, this is another seismic profile from the same volume. So here we have the depth section, the decompacted section, and we have the one-to-one section as well. In this example here, Mike was able to map two horizons in the contractional domain, a lower one, which is called C1, and an upper horizon, which is called C2 in through here. When he looked at the amount of shortening in the lower horizon, so this is the one I'm showing you in here, this gave a percentage shortening using the same methods as in the previous slide of around about 25% shortening. So that's deep within the submarine landslide. A few hundred meters above in the submarine landslide at this C2 level in here, so that's this level here, there is considerably less shortening. Okay, so we see less shortening seismically expressed in thrusting, expressed in the seismic expression of strain, that's thrusts, than we see. And remember, all we're able to do here is look at the seismic expression of strain. I'm going to come on to now why that's important, because we do see a depth discrepancy of around, let's say, 10%. So we have a longitudinal discrepancy and a vertical discrepancy in strain. So why is that? Well, let's look at these big submarine landslides here. This is a massive one on the Orange Basin offshore Namibia. You can see the scale bar in here in two-way time. Here's an area of extension, and it's slipping here on overpressured muds, and here's this domain of contraction down dip. And Butler and Payton did a similar exercise to what we did. They measured the amount of extension up dip and saw it was around about 44 to 48 kilometers. And they also looked at the magnitude of contraction down here and saw it was between 18.5 and 25. Critically, the reason I've colored these green and blue is because the amount of contraction at the lower level was less than at the upper level. So similar to what we saw in the Uruguayan small submarine landslide example, there's this vertical strain discrepancy as well. So overall, there's a longitudinal discrepancy of around about 18 to 25%, but there's also a vertical discrepancy in the contractional domain. So why is that? Well, one reason may be the kinematics occurring as the material is moving. We start off with an uncompacted amount of sediment near surface, which is very wet and has high porosity. We then shorten that, and we can shorten that because we have extension occurring earlier in the system up dip. What we then have happening is what's showing here in these animations, what we call cryptic compaction. We actually start to squeeze the grains horizontally, expelling pore water and reducing the porosity before we then finally manifest a thrust. So we embrittle the strata to make it brittle enough to take a strain, which is discrete, in this case a thrust, and then we're able to actually have a thrust. So we have a lot of shortening. Experimentally, and also based on some other studies, it's shown that you can have up to about 23% of horizontal shortening in things like carbonates as well as sedimentary rocks, clastic rocks, before you actually see a seismic expression of strain in the form of a discrete structure. So that's why we think quantifying strain is important, because it does allow you to try and understand some of the kinematics and then perhaps the mechanics. So let's move away from the kind of large scale strain and start to focus in on the erosivity and deformation occurring at the bottom of these slides. And I'm going to show you here some of Hari Anugraha's PhD work, where he came up with this thing called the VD-VE ratio. So let's have a look at this using this seismic data set here from the Northwest Shelf of Australia. You can see here this seabed in here, beautifully seismically imaged body in here, really kind of seismically chaotic submarine landslide down here. And that's the VD, that's the deposit volume down dip. We then can look at restoring the paleo seabed before the failure that fed this deposit and I'll show you in a couple of slides how we do that, and that yields the VE. So that's the evacuated volume. I'm showing you in 2D here, but we can actually get to this obviously in 3D with 3D seismic reflection data or closely spaced 2D data. So why is that important? Well, if we have a VD volume of less than 1, so the deposit volume is less than the failed volume, that could mean that we have some material leaving the flow as it's moving. If we have a VD and VE ratio of 1, there's no volume change, and that could mean that the flow is hydroplaning, so it's not taking in material, it's not losing material. Or it could be eroding the seabed, but actually losing some material in a kind of low density cloud. So, but overall it balances to give us this ratio of 1. Or we could have a VD-VE ratio of more than 1, where there's actually large amounts of erosion into the seabed. You're cannibalizing the seabed and taking that material into the flow. So you're bulking it up. You could change its rheology. But in terms of geohazards, think about it, you're making that flow become progressively bigger and potentially more powerful than the kind of failed volume would suggest it would be. So we did this analysis looking at the kind of present day seabed and the immediately subseabed strata offshore Australia. So here's a present day seabed map. In here you can see the area of the failure is in here with these beautiful cat claw scours at the base in here. And this is an area of the unfailed slope along strike to the south. And you can see on this seismic data set here, this seismic profile, there's no failure here. You've just got this nice cliniform geometry, which is the last cliniform progradation above all of these cliniforms. But if we go along to section C, just in here where this landslide has occurred, that's where you see the big bite has been taken out of the shelf edge in here. So this is all the material that went down to feed the submarine landslide that we looked at a couple of on the last slide. When we do this calculation, we actually see something which I was completely shocked by, to be honest. Depending on which method you use, there's a few different methods. I'm not going to go into them today. You can read Haria's paper if you want to find out the different methods, because there are different ways of calculating this. You see that the VD-VE ratio is huge. It's way more than 1. At best, it's 5, and that, you know, kind of the more realistic values, which are quite close together, is that the deposit volume is 15 times the size of the originally failed mass. So this thing we call the Gorgon slide is strongly erosive. We played around with numbers. I told Haria he might have been wrong, and we couldn't get away from the fact that this ratio was just very, very big. When we went and looked at examples around the world to kind of convince ourselves we hadn't completely lost it, there are only about 11 or 12 examples where people have provided both the failed volume and the deposit volume in terms of volume. So it's not time migrated data. They've used depth migrated data, or they've used time migrated volume data and actually done a depth conversion to get actual volumes in kilometers cubed. When you do that on these case studies around the world, what you see is the VD-VE ratio for all of these case studies shown here on the kind of y-axis. The VD-VE ratio is going from 0 to 16. You see that quite a lot of them have a VD-VE ratio of way more than 1. A median of 2 and a mean of 3, and the Gorgon sits out here all on its own as this weird carbonate ooze type submarine landslide. So maybe a lot of these deposits are actually very, very bulky. They've bulked up, and that's not surprising when you look at the base of a lot of these submarine landslides, that there's a huge amount of erosion at their basal surfaces, as shown here on another example from Nick Scarcelli from offshore Australia. So these deposits are not simply these currents, I should say, not simply hydroplaning, but they're actually kind of eroding a large amount of material from the seabed. So like I said, this has implications for geohazard analysis in terms of trying to understand, well, we've defined this area as potentially being an area of failure, but then you may have to multiply that number by between 3 and 16 to get to the volume of material that might be impacting seabed infrastructure, or what could potentially trigger a tsunami. But what's really going on in the basal shear zone? And this is where I'm just going to finish the talk with one last case study where we're going to really drill in to the details of that basal shear surface or basal shear zone in terms of the processes. And to do that, I'm going to highlight some of the work of Nan Wu, who is a complete superhero, as shown here in this photo of him. And Nan got his teeth into lots and lots of different things during his PhD, and one of which was this data set from the northern Gulf of Mexico. So this was a really nice data set. We had this big 3D seismic volume, as you can see in here, the scales in here. This is 2 kilometers. This was the depth migrated volume again. And we had this well drilled by Shell from the 80s, I think it was, which actually penetrated all the way down through, as you can see colored in here, a number of different mass transport complexes or slides. And we had a full well log suite as well to go with this. So let's zoom into Mass Transport Complex 2. That's this one here, the green one, right in the middle of the profile. Here's the well data. I'm just showing you on here the density and the gamma ray data, sorry, in there. And there's the basal shear surface in yellow. You've got these nicely layered strata underneath, the chaotic strata, the strata characterizing the slide, and then we've got layered strata, slope strata above as well. And actually in this case, it's quite nice. There's this thing in here is actually what we call a remnant block. It's a block which has sort of been overridden by the downslope traveling slide, or mass transport complex as we call it in this case. So let's now go and have a look at lithologically and petrophysically the mass transport complex that's been drilled in this position. So here it is. What I'm showing you in here is depth. This is a bit small, so I'll just talk you through what's here. This is 40 meters. 2 of these notches are 40 meters for scale. So this mass transport complex in here is around about 150 meters thick. So it's quite thick in this position. What I'm showing you in here in the y-axis is VP. So this is the velocity, and those data are plotted in blue. And on the bottom here are the resistivity in here, RT, sorry, not density, resistivity. And that's in the green dots in through here. The basal shear surface of the deposit is marked in yellow to match the seismic profile, and the top of the deposit is here in green again to match the profile. What you can see is quite a lot of variability in through here. Cuttings in the well log data suggest that there are sands in this mass transport complex as well as mud. But what I want to draw your attention to is right at the bottom of this, in the lowermost 15 to 20 meters in here. You can see that both the density, sorry, the resistivity and the velocity both take a marked increase. And we see this in a number of the slides. The lower bit of the deposit is acoustically faster, but also more resistive, suggesting that the porosity is lower in that lower 20 meters. So compare those mudstones here, the grey colour, with the mudstones higher up. There's quite a step in the acoustic velocity of around about 200 meters per second. And we see that in a number of different units penetrated in this well. So that's what we've interpreted as being this basal shear zone, not a discrete surface, although seismically that's what we think there is. There's actually probably a zone of enhanced shear, or well, let me back out. There's a zone of distinct physical properties. So this is just to show you that we, you know, the one we looked at before was this one in here. Sorry, this was Mass Transport Complex 2. This is 3 up in here and 1 down at the bottom in yellow. And I've just highlighted on there these basal shear zones, and just to show you that you can see very nicely that big step in the density and the resistivity and the velocity. So what does this mean? What do we get then? Having quantified this, what do we get kinematically about the processes going on as this material is traveling across the seabed? Well, what we think is happening, we've got this relatively cohesive flow, and we have this zone at the bottom within which we've got enhanced shearing. During the early phase of the flow, we actually probably have liquefaction as we overpressure. We load the seabed, water-wet seabed or near seabed material with that heavy body. We then actually then have pore collapse and water escape, and we get that porosity collapse. Before then we have overcompaction. So we see that 3 phases occurring in one position as it's being overridden, but also longitudinally within the same flow. And that's what leads to what we see petrophysically here, this increase in velocity and this increase in resistivity and decrease in porosity in this basal shear zone.
2 minutes, Chris.
Okay, almost there. Also, this is the more speculative bit of the talk, is one thing we got very excited about, but we didn't really get confident enough to push it as far as we should, is can we then invert that for seismic, or then can we invert that for seismic properties, which then we could use to invert backwards from seismic properties to porosity. So let's take this example here. We've got undeformed slope strata here. We've got these velocity and density characteristics for this upper mud, and this properties for this lower unit in here. If we then calculate acoustic impedance, reflection coefficient, trust me, I've done the numbers, that's what you get, a weak positive response at that boundary. But if we come along here to where there's an area where the same materials are overlain now by a highly sheared basal shear zone and a highly sheared body of a mass transport complex or slide, notice here the density and the velocity are higher than here in the undeformed section, but the lower materials are the same. We actually get a weak negative response. So we could actually seismically see, and we see that in the seismic data, we see this change along the basal shear surface in both possibly polarity, but also in reflection strength. And when you make a seismic amplitude map of the base of some of these deposits, you can see here on the right-hand side of this white dashed line, this higher reflectivity than here on the left-hand side. So there are some changes in the acoustic properties as a function of the changes in these petrophysical properties. And we think that's an exciting avenue for work. So to finish, by doing this quantitative stuff, which I don't normally get my hands dirty with, but it was very exciting 4 years ago to think about how could we apply these things to slides. We can look at intra-slide strain variability and how this relates to the rheological properties and changes in the flow as it evolves. We've noted that the slides can be very erosive and that this has implications for geohazard assessment, and that these slides are likely underlain by a more diffuse type of shear zone rather than a very discrete shear surface, and that this strain hardening can lead to differences in the sealing and fluid flow properties at that boundary. So thank you very much.
Thank you very much, Chris. That was really interesting. Some really great work by yourself and all of the early career researchers you mentioned. So now we will wait for some questions. Hopefully anyone that has questions, you maybe put it in the chat. Seems we have one already from Mikkel. Great talk, Chris, thanks. Did you compare the VD/VE values from those case studies to the lithologic composition of the seabed? And if not, how do you think seabed lithology could influence them?
Yeah, we did. So in the plot, sorry, if I can just quickly do this, I'll show you. Yeah, so in the plot, we compared, sorry, I'm just trying to find it here, there we go. So you notice in this, you can see Mikkel hopefully here, siliciclastic are in yellow, carbonate are in blue, and the oranges are where there was a reported mixed lithology. And we had the only one which was composed of these carbonate oozes. So we wonder whether or not it's something to do with the physical properties of these carbonate oozes that mean that they are more highly erosive because you have very extreme pore collapse and ingestion at the base of the flow versus these clastic deposits in here. But, so yes, we did, to answer your question, yes, we did separate them. Is this enough data to draw a conclusion about the rheological properties as a function of seabed lithology? I feel not competent enough to do that, but it is quite interesting at the moment.
Yeah, that's interesting. And did you look at the slope gradient as well in terms of that erosivity? Or?
Yes, we did. So Harrier looked at slope gradient, and again, that's in the paper in the chat, which Valentin's probably posted. And that doesn't seem to be the main control on the erosivity or change in slope.
Okay. Yeah. Okay, we have another question from Lucas. Do you think that intergranular shear mechanisms could be related to the observed variations in basal shear properties?
Yes, I would think so. And it might have to do with the, I guess, the original cohesion of the material at the seabed. So if you already have quite high cohesion in mudstones because of interparticular forces, then maybe it's going to, you've already got quite a hard seabed versus much more weakly bonded materials, which may be more subject to shear. And whether it's shear hardening or whether you actually are able to have some turbulence within the overriding flow that can bring that material up into the flow, I don't know, but hypothetically, the rheological properties and the mechanical properties of the seabed will control how bulked up the flows get. And also the other thing I should have said is how far the flows can run out. Because if you're adding more density and more volume to the flow, then you've actually got more gravitational potential by making them bigger. So they could run further on even a low gradient seabed.
Yeah, thank you, Chris. While we wait for a few more questions, I noticed that we have posted in the chat some references to all your excellent work, you and your students. Looks like we may have another message. Great talk as well. I guess I can ask you another question, Chris, while we're waiting. What are your plans going forward in this area of research now? Are you having more studentships? What sort of area are you going to be focusing on?
Yeah, so we are, and so Mike Clare, who's one of the co-authors on here, we've talked a bit, and also with Lorraine Moscardeli, about kind of continuing work on submarine landslides as relates to subaqueous geohazards as well. So I think some of the work that Harriet did around the erosivity is really interesting, because it goes to the two questions we had about whether the seabed lithology and the rheological properties actually control the run-out distance and the amount of ingestion of material. So yeah, we're probably going to have some more projects looking at that. One thing would be really exciting to look at is the IADP data, because there's large IADP data sets with very well calibrated with seismic sort of near surface things, which would allow you to do more. I mean, this data set was quite unique that NAN worked on, because we actually had some well data going through a stack of MTCs because they were above a prospective depth. But the Harrier's work is only calibrated by an offset IADP well. So we struggle there to really pinpoint what the kind of seabed materials were like prior to the emplacement of the material, or what they look like now at least. So yeah, we're going to try and look at some more examples where the borehole calibration is better.
Yeah, I'll watch this space then.
Yeah.
We have another question. It's good. Great talk on MTC, thanks. In seismic studies for lithologic sensing, velocity impedance is good. For fluid escape, did you or your team try gradient impedance?
No, we didn't actually use gradient impedance. The map I showed there quickly at the end was actually a maximum negative reflection strength attributes. So no, we haven't tried anything else yet, because like I said, it was quite tentative. We didn't think anything was going to come of it, but then when we started doing these maps, we actually saw this change in reflection strength at the bottom. So that is definitely an avenue for further work, is to see if you can characterize them seismically, because what you really want is to be able to predict the properties in the absence of a well, because you want to know that before you drill the well, what the properties of the basal shear surface are.
We have another one. Amazing work, Chris and co. Do you think the landslides in these examples happened as instantaneous failures or more progressively? And if they were progressive, do you think that deposition occurring on top of the slide during the sliding event might increase the VD-VE ratio?
It sounds like this is the person who reviewed Harry's paper.
Dan?
Yeah, so we think that, well, some of these events we think are instantaneous. Some of them it's harder to know whether or not they're progressive failures. So you've actually got a stack of landslides. So that's why we use the term mass transport complexes, because we're not sure whether there are a number of individual deposits or associated with a number of separate events. In a couple of these, we think that they're, in the Gorgon slide thing, we think it's definitely an instantaneous event. Whether that would increase the VD-VE ratio, my gut feeling is that it wouldn't, because you'll still be adding the composite VD with the composite VE. The only way you would be erroneous is if maybe if you had two inputs into the basin and there was a failure on another flank you were unaware of, and that was adding VD that you weren't capturing in your VE, right? If that makes sense. Even if you've got some kind of retrogressive slope failure mechanism, I think you would still add up all that volume. But I'm happy to chat about it later on. That's just my gut feeling.
Yeah, excellent. Okay, well, we're at the end of the slot. That's okay, Chris. Thanks again. It was really great.